Have you ever really thought about that? How does your phone know it's getting too hot? Or how does a simple thermostat know exactly when it's time to kick on the AC? Well, it's not some kind of magic, it's technology. It's about giving machines a sense of touch, a way to feel one of the most basic forces in the universe, heat. So let's get into it.
And that's exactly what we're going to do in this explainer. We're going to meet the unsung heroes of our modern world, temperature sensors. We're going to break down how these little devices work, everything from the super tough ones you'd find in a blast furnace, all the way down to the tiny circuits that are probably sitting in your smartwatch right now. So here's the game plan. First up, we'll nail down what a temperature sensor actually is. Then we'll see how they all fall into two main camps, contact and non-contact. After that, we'll meet the experts in each category, put them head-to-head in a spec showdown, and then finally, we'll figure out how you pick the absolute right sensor for any job. Okay, let's start at square one. What are we even talking about here? Well, at the end of the day, it's all about turning an invisible force, temperature, into something a machine can actually understand and use. It's about turning a feeling into data. So at its very core, a temperature sensor is basically a translator. It takes heat, something that we can feel, and it converts it into an electrical signal, a voltage or a resistance. And that signal is everything. It's the piece of data that lets a system keep an eye on itself, log what's happening, or even make a crucial decision, like, hey, I should probably turn on this fan before I melt. Now, when you look at all the different kinds of sensors out there, they pretty much all fall into one of two major families. And the difference really boils down to one simple question. Do you have to actually touch the thing you want to measure? And here they are. On one side, you've got your contact sensors. These are the hands-on types, right? They have to be in direct physical contact with an object to get a reading. Then, on the other side, you have the non-contact sensors. Think of these as the scouts. They can figure out the temperature from a distance, usually by detecting the invisible thermal energy an object is giving off. All right, let's dive in and meet the contact lineup first. You can think of these guys as a team of specialists, and each one has a totally unique way of getting right up close to feel the heat. First up, let's talk about the thermocouple. This one is the seasoned veteran of the group. It is tough, it's reliable, and you are going to find this thing in some of the most extreme industrial environments you can even imagine. So how does this old timer work? Well, it's based on a really cool principle called the Seebeck effect. Basically, if you take two different types of metal wire and join them at one end, and then you heat that junction up, you actually create a tiny measurable voltage. The hotter it gets, the higher the voltage. It's this beautifully simple and incredibly robust idea that lets thermocouples handle a massive range of temperatures and survive inside things like furnaces and jet engines. Next on the team is the resistance temperature detector, or as everyone calls it, the RTD. Now, if the thermocouple is our rugged veteran, the RTD is the meticulous lab scientist. For this one, it's all about precision. The RTD's secret is actually pretty straightforward. Certain metals, like platinum, change their electrical resistance in a super predictable way as their temperature changes. So by measuring that resistance very carefully, you can calculate the temperature with incredible accuracy and stability over time. It's no wonder they're the gold standard for scientific labs and any industrial process that needs to be spot on. Okay, let's meet our third expert, the thermistor. This one's a specialist in sensitivity and speed. It can react to the absolute tiniest changes in temperature, and it does it really, really fast, which is exactly why you find them everywhere, from your car to the digital thermometer you have at home. So unlike the RTD, which uses metal, a thermistor uses a semiconductor material. And here's where it gets really interesting. Its resistance doesn't just change with temperature, it changes dramatically. We're talking a huge drop or a huge spike. This massive shift makes it incredibly sensitive to even small temperature changes, although it works over a narrower range. Its low cost and high sensitivity make it the perfect choice for tons of consumer electronics. And last but not least, for our contact team, we have the modern prodigy, the semiconductor sensor. This is basically a whole smart sensor built right onto a tiny little chip, and it's designed from the ground up for the digital age. Yeah, these little guys use the fundamental properties of a semiconductor junction. The voltage across that junction changes in a very clean, linear way with temperature. And the best part, all the extra circuitry needed to read that is built right onto the same chip. This makes them super easy and cheap to connect directly to microcontrollers, making them the superstars of embedded systems and IoT devices. All right, so we've met the whole contact team. Now, it's time to take a step back and meet the specialist who doesn't need to get close to the action at all.
Say hello to the infrared, or IR, sensor. This is our non-contact scout. It can tell you how hot something is from all the way across the room, which, as you can imagine, is unbelievably useful when you're dealing with things you can't touch or, really, really don't want to touch.
The key thing to get here is that basically every object that isn't at absolute zero is constantly glowing with invisible infrared light. An IR sensor is, for all intents and purposes, a special camera that can see this thermal glow. It operates on something called the Stefan-Boltzmann law, which is just a fancy way of saying the hotter something is, the brighter it glows in infrared. The sensor just measures that glow and calculates the temperature. It's perfect for things that are moving, like on a conveyor belt, or things that are crazy hot, like molten metal.
Okay, we've officially met the entire team. So now it's time for the main event. Let's put them all side by side and see how they really stack up against each other. It's time for the ultimate sensor showdown. And this table really tells the whole story, doesn't it? It's all about trade-offs. You need to measure a massive temperature range, but you're on a tight budget? The thermocouple is your guy, no question. But what if you need the absolute highest accuracy possible, and cost isn't an issue? Well, then you have to go with the RTD. For most everyday electronics, you can see why the low cost and high performance of thermistors and semiconductor sensors are a perfect fit. And of course, if you can't touch what you're measuring, the IR sensor's speed and safety make it the obvious choice.
So, as you can probably tell by now, there is no single best sensor. It just doesn't exist. The perfect choice always comes down to matching the right expert to the specific mission.
And here's the real takeaway. When an engineer has to choose a sensor, they're always balancing these 5 key questions. How accurate do I really need to be? What's the hottest or coldest it's going to get? How fast do I need to get a reading? What kind of crazy environment is this thing going to live in? And, the big one, how much can I spend? The answers to those questions will point you to the perfect expert for the job every time. When you think about it, from jet engines to our own bodies, these sensors are giving technology a fundamentally human sense. They let our world react, adapt, and even protect itself in real time, which really makes you wonder, as these tiny, powerful sensors get embedded in pretty much everything around us, what new things are we going to learn? What is our world going to be able to feel next?